All right, so part of this is going to be really techy. Stop me anytime and raise your hand. Questions, I would really like to get questions as we go. And I want you to, learn some of this stuff. Some of it's really about numbers and techie stuff, and some of it's really not. And I've got some interesting examples there at the end. So, yeah, ask questions. Why bother? This is actually an ad out of a magazine. This is an ad for an SUV. It came out of the New Yorker a couple of years ago. I probably don't need to talk to this crowd about why bother. There's a really good resource that you can Google, John Straub's presentation at Better Buildings by Design 2013 that's also about mechanicals. And he has, of course, a little bit different take on things, and I robbed some things from him too, which I do frequently. He's very generous that way. So there's a good resource there, and I'll make this available as a PDF, and you'll have this for folks too? Yeah, so, okay. So I'm going to look at kind of super low load homes to efficient homes, and somewhere in the middle. I would say most of the houses I do are really in this zone. And, getting a little toward this zone, but mostly right in here. And, we're looking at moderate size houses here for the most part.
What do you consider moderate?
Sorry?
What do you consider moderate?
Moderate size houses? Yeah. A couple thousand square feet for 3 or 4 people.
Okay.
Something like that. So I want to make a distinction here, which we're going to use this later, of load versus energy. So load is what's the amount of heat you've got to put into this thing over the, let's say, the course of the winter to keep it warm. And energy is how much fuel you require to do that. They're really two different things, because you burn the fuel, you lose some up the chimney, right? So you need more fuel, more energy usually than load, unless you're a heat pump, but we'll talk about that. And then there's demand. So how fast does he have to stoke this on the coldest day of the winter? So that's the peak heating demand. And I don't think we'll talk too much about cooling. Is anybody interested in talking about cooling? So so these really, just some numbers, these really low load houses, 3 to 8 BTUs per square foot per hour for a peak load. These micro load houses are, a little bit more. Efficient houses, a little bit more than that. So these, you're practically heating with light bulbs, a few light bulbs. Here you need something that's going to put out some heat, and here you need kind of a bit more. This was some work that Rhiannon did at Bensonwood for this new line of homes they had, these Unity homes. They're doing some really interesting stuff there. If you've never checked out their stuff, it's really interesting. They're building homes in a factory. But kind of typical construction practices, but they can just mechanize the whole thing. They've got 3D drafting that then sends the cut list to the numerical cutting machine that you feed pieces of wood in, and it cuts the right pieces and stamps them with numbers, and they're all put together really well with gaskets. They're getting super low air leakage rates on these things, and doing some really interesting stuff kind of right in here. Very low, 10 to 20,000 BTU an hour total peak load for a house, a typical house size like this. I think that one's 1,800 square feet. So what are we talking about for these different levels of efficiency? So, so passive house. How many people are familiar with or have heard of passive house? Okay, so this has gotten to be sort of the gold standard on efficiency. And I get a little cranky with it because I think there's places they overspend on the insulation, or places where you could buy PVs cheaper than adding that next increment of insulation. So, but anyway, I've more been designing in this range, sort of micro load, kind of R5 windows, R20 earth contact, R40 walls, R60 roof. Pretty low air change rates, 1 to 1.5 air changes an hour at 50 pascals, which is a test pressure. These guys are very low. air leakage rates are 7 windows. These start to get pretty pricey. 30 against the ground or more sometimes, 50 in the walls, 80 in the roof. And it's an interesting question about should you invest more than this and go to this level, and what do you get from it? And we probably won't get into that today, unless somebody really wants to. So efficient buildings, there maybe are 4 windows. So these are probably triple glazed windows, but maybe just 1 low E layer in there. Whereas this would be a triple glazed window with 2 low E layers. This could be a quad glazed window, sort of 2 layers of suspended film with low E coatings in there and maybe krypton gas in all 3 cavities. Very well insulated window frames, very pricey stuff, and just more insulation. Maybe 15 in the ground. I think that's code now, right? Isn't that the new energy code, 15 earth contact? 30 walls, 40 roof. That's more sort of what we've been doing the past decade. So, what do we need? Need to stay warm, stay cool in the summer, not freeze in the shower, and have fresh air. So, how do you pick? The first part is really about the goals. What are your goals here? What are the owner's goals for the home? And we'll get into that some more. And then what are the needs aside from the goals? What are the opportunities and what are the constraints? So we'll talk some more about each of these. I try and get people that I'm working with to really sit down and talk about what are their goals for the building? What do they want to have happen? It's easy to get people to talk about, I need a living room, I need a dining room, I need it this big, I need the office. But how do they want their building to relate to the planet? How do they want the indoor, what do they want in the indoor environmental quality, which encompasses air quality, light quality, thermal comfort. And if you can get people to really express what those things are that they're after, it really helps them then define exactly what it is, or helps the designer really give them what they're looking for, and gives you some guideposts. And without that, it's pretty hard to figure out where you're going. These can range all over the place. And you're gonna put this down. I like to sort of with somebody I'm just meeting, I kind of try and say, where's their green meter here? Over here is like, just get me something. I've got a low budget. I've got a fixed budget. I need to get into the building. Up here is kind of stop shooting yourself in the foot. Don't put it together so you've got $1,000 heating bills. Then we've got sort of cost-effective investment, and that what's cost and what's effect varies a lot for people, but it's probably gets you to that efficient building level. And then people want really a high degree of comfort, really low energy use. We get to the micro load level. People then maybe say net zero, I want a zero carbon building. They're kind of over here. The green meter's kind of pegged. I want zero carbon. I want this as low energy building as possible. And so it's important to kind of figure out where people are on that spectrum so you can, these systems can really work with that. So might be somebody says to you, I want the lowest possible energy. Well, lowest possible is kind of zero, but that's okay. It just needs some clarification. Might be it's a net zero building. Might be they're interested in zero carbon emission more than they're interested in low cost, low operating cost. Low installed cost is often a criteria for people, and good quality inside environment. So it's good to try and suss this stuff out and pull it out of people. And somebody here who's about to start on a project for their own home, pick where you would be on here.
All of it?
Yeah, probably not. Probably can't. You probably have a hard time getting this one and this one. This is good, fast, and cheap. And it's like we're not getting all of them. No takers?
I think I'm still trying to understand for myself what the differences between all of these. I mean, I understand Well, I guess it's zero carbon versus low CO2 emissions, I guess. Perhaps that's my difference there.
Uh-huh.
Um,
Yeah, so, and then, like you said, what are the implications? What's this going to mean for what I have to put in and what I have to spend? And so it's going to go back and forth, and at least you can start with your dreams, and then as the realities kick in, then, you know, building a house is brokering between your dreams and your realities. And it's good to start with your dreams, so at least we know where those are. So what are the needs? Do we need point source or zoned heating? Do we need air conditioning? How much zoning is going to be required in the house? How tight a temperature control do you need? And then how big are the loads? So these are the needs, really. What are the opportunities? What are the fuels that you have available to you? Do you want it all electric? PV? Is there solar access? And what are the constraints?
So can you just, I mean, this is again my ignorance, the difference between PV powered and all electric?
All electric you can plug into the grid and not have any PVs at all and still have an all electric house.
But PV can be grid tied too.
Right, but at least it could be, you would be making at least some of your electricity. So I've done houses that have heat pumps for an electric or solar hot water or heat pump hot water, but they don't have PV, so they're all electric,
Oh, okay.
but they don't have any PV power for it.
Okay.
Is there another handout? This, any of you ever seen, how many of you have seen one of these things? Yeah, most everybody. It's a, whoops. I can't breathe here. This is a neat widget that, these are the path of the sun during the day, so at the hours of the day, this would be in the summer, this would be in the winter. And this little glass dome reflector, you set this thing just right and point it south, and it tells you what hours of the day this site would be shaded, and this site would be shaded quite a lot. So, you know, understanding this stuff up front about what your constraints
How
are.
can the hard water be a constraint? In what sense?
It'd be a constraint for passive solar heating in the house, and it'd be a constraint for active solar. Because you would only have, in the middle of the winter here, you'd only have sun between, what is this, 11 and 2 for all these winter months here. Summer, you'd get a band of clear here and a little bit in the afternoon.
He was asking about the hard water.
Hard water.
That would be a constraint.
Sorry. Hard water is a constraint on what you can use for heating your hot water with. So an instantaneous hot water heater gets really unhappy with hard water. And you need to look in the manufacturer's literature to see how many grains of hardness. And even if it's a little hard, you got to put flush valves in there and you got to clear the thing out because it intensely heats the hot water in a very tiny tube. Intense heating makes minerals precipitate out of the water. And of course the little tube is a problem because it gets clogged up quickly. So that's one of the big constraints on water. It can also be an issue if you're running a heat pump, a ground source heat pump out of well water. Well, sometimes not as much of an issue. You know, our folks in the home have allergies, so that'll influence what your pick is on the systems too. So, for example, some folks with allergies want nothing that catches dust, so you might go for a radiant floor instead of a baseboard hot water system. Some folks with allergies don't want air blowing around. Some folks with allergies would rather have the air blowing around so that they can run it through a really high efficiency filter. Fuel costs is going to be another piece that you'll want to look at. I'm really not touching that button. So these were just some costs I picked for all these different fuels. Natural gas, of course, we don't have to worry about that here. Cordwood, wood pellets, a heat pump using electricity, oil, propane, and just straight resistance electric. And after you account for the cost of the fuel and some average efficiency, you can look at what does it cost you per million BTUs delivered energy. Well, natural gas is cheap, cordwood is cheap. Wood pellets are pretty close here, which is interesting. They're more expensive to buy per unit of heat, but you can burn them much more efficiently than you can cordwood. Heat pump with electricity, this is interesting, it's really cheap. And the reason is we can get a coefficient of performance out of it, meaning you can get 2.5 units of heat, give or take, for each unit of electricity that you have to buy. Up here it's a little lower, like 2.3 maybe, but around 2.5. So the operating cost is really pretty low. It's pretty close to wood, which is pretty amazing. Oil and propane, of course, are double everything else. And just straight resistance electricity is really expensive.
What do you mean by after combustion? On the right hand.
Let's take a look at natural gas. You can get equipment that'll burn that at 90% efficiency.
Okay.
So there's 0.1 million BTUs per unit, but you're only going to get 90% of that into the house.
Okay.
Mm-hmm.
What about geothermal?
Water-to-water heat pumps are right around here, around a COP of 2.5. So that would be here. If you had a more efficient system, if you could get it up to 3.5, which some of them do, that cost would come down to, I don't know, probably 14 or so, or 13 or 12, somewhere in there.
Is that any of that calculated with cooling, or is that just?
That's just heating.
And the costs are all just calculated and operating on the installation,
Right, we'll come to the installation costs. These are just operating.
so that ground source heat pump would be a lot more expensive under here.
And we'll look at that in a minute. Mhm.
I was just saying, it's interesting that natural gas is so much cheaper than propane.
Yeah. Propane is a real sneaker. And also the delivery system for propane is just all over the map. They charge you, they own the tank, then they have you captive, and they can charge you whatever they want. And when you try and switch out the tank, which they own, then they want to charge you to get rid of the tank. And I'm not sure why it's such a racket compared to oil, but it is. So if people are using any more than just the tiniest bit of it, they should own their own tank. Then you can go call somebody and get a price, you can shop around for a price. So what about the CO2 emissions from these fuels? So here's pounds of CO2 per million BTUs at the site. So natural gas is, it's got a fair bit of CO2 emissions. Cordwood, very low. And this really, I'm considering that the cordwood itself is zero carbon. So maybe it's a 50-year cycle that it's getting carbon from the atmosphere over 50 years and then we're releasing it back again. So I'm considering that zero. Not everybody does. But this little bit of 3 it takes a little bit of gasoline and so on to get the wood there. Wood pellets on site, 60, very low. There's more fossil fuel essentially goes into making the pellets. They're trucked. The sawdust is trucked. There's a manufacturing process. They truck you the pellets. It can be anywhere between 7 and 15% of the numbers that I was able to find of the total energy in the pellets. That equivalent of 7 to 15% of that energy is spent in fossil fuel. So it's not pure, but nothing is. Electricity on site, there's no carbon emissions. Oil, of course, and propane have the highest. But now let's look at the primary energy. The primary energy is all the energy that went into the system, and in the case of electricity, all the waste energy at the power plants. The power plants are roughly 1/3 efficient. 2/3 of the fuel goes into them, plants that burn something or heat something. 2/3 of the energy is going up the stack. So now all of a sudden, this electricity used on site, if we use it for resistance, it's huge. It's the biggest carbon emitter. Now, if we use it with a heat pump, we can cut that down by, here I cut it by 2.5, we maybe get cut it by 3, and we can get it lower. But it's still quite a bit higher than wood. And interestingly, it's not all that different than natural gas. So if you're doing a heat pump, and you're plugged into the grid, you're not doing it to save carbon. It's not going to save carbon. And the heat pump folks kind of glossed this over a little bit. Does that make sense? Is that okay? Is everybody okay with that? So then would you do a heat pump if you were interested in low carbon? How could you do that? PVs, yeah. So here's my sort of general list for things to think about with mechanicals. General principles. Capture waste heat flows. We're going to talk about this. People need fresh air. It's just the price of living in a box. Use renewables. If you're burning stuff, seal combustion. Houses now are tight enough, if you're saving energy, that you can't afford to have backdrafting in the houses. Keep the owner's goals in mind as you're going through. Keep the systems as simple as possible. And now with these really low load houses, I went to a house the other day, they had, I don't know, $35,000 worth of ground source heat pump in this little tiny house that maybe shouldn't cost more than $500 or $800 to heat for the year. It's like something's wrong with the picture. These things are great. Do you have one of these here, rainwater heat recovery? No. These things are really cool. Let me see if I get an actual picture. Yeah, okay, so anybody, raise your hand if you have not seen one of these. Okay, then I'll explain it. Okay, so this is a drained line, and it comes out of your shower. Here, it's coming out of the shower down here. And then you put in this 5-foot tall piece of copper drain pipe. This one I think is 3-inch. And then it connects to the regular drain pipe at the bottom. And then what's wrapped around it is more copper pipe intimately connected to the inside piece. And when you're drawing hot water, of course, cold water has to feed into the hot water tank, right? And that's directed through this coil. So you're recovering a really good chunk of the energy that's going down the drain. You know, think about it. You're standing under a shower. You maybe have 105-degree water coming on you, and you're dumping 90-degree water down the drain. So you're dumping, you know, 3/4 of the heat or 80% of the heat. So this thing will recover maybe half of that. And if you can arrange it, you need this 5 feet of height between the bottom of the showers and where the sewer goes out, or septic goes out.
And is that usually is insulated on the outside of that? I'm just kind of curious.
Well, you know, it's pretty low temperature.
Okay.
So we might be taking the 40 or 50 degree, 50 degree, 45 degree water and running it up to 70 or 80.
Okay.
So it's
Yeah.
hardly worth insulating.
Yeah.
Yeah, there's a schematic. So the trick is it doesn't work for a bathtub, right? Because you fill at one point and dump at a different point. It has to be for a shower where it's going at the same time.
How does that work in terms of, is it like the water going down through the main tube and then coil with gas within it?
No.
Circling that, or is the water actually going through those?
This is cold water going through these outside pipe, this outside tubing.
Okay.
It's the cold water that's going to feed your hot water heater.
Okay.
So you're preheating it. The thing that makes this work, which I never realized, was that, you know, I always thought if you had a pipe like this and you're dumping water down the drain, it was like a ball that fell down the middle of the pipe. Well, it doesn't do that. The surface tension makes the water stick. And that was the basis of the first patent that somebody tried to get on this thing. He called it a falling film heat exchanger. So the water sticks to the pipe. So the hot water is running down the surface of the pipe. And that's what really makes this thing work.
What's the payback like on something like that?
Oh, it's great. I mean, the unit costs what, $500-600?
Sometimes less. Depends on, yeah.
I mean, you could get it in for $1,000, let's say, and you could get, if a lot of your load is a shower, you might get 1/3 of your hot water for $1,000. I mean, compare that to a heat pump water heater that'll do half of it for $2,000 or $3,000, or a solar hot water system. You know, I have this coupled with a solar hot water system in my house.
There's no mechanical moving parts. It's not going to wear out.
Right.
So you put it in, and it's zero maintenance for the life of the building.
Some people feel like Henry Gifford down in New York, he says he's taken apart pipes in apartment buildings where they get coated with gick on the inside. And, you know, so it's probably worth putting a clean out up here just to be able to clean it out at some point. I've never maintained mine. I should probably be a good research project. Is the efficiency now worse than, or is it worse later than at the beginning?
And hard water could be a problem there too, because you get calcification inside the copper, and you get minerals.
In the inside pipe?
In the copper supply line there, which would reduce the heat transfer efficiency, the same as in a instantaneous heater.
Yeah.
This is a lot of surface area there.
Yeah.
Is it still practical?
Temperatures are lower, so it wouldn't be as bad as a,
Lower, and you've got stuff in suspension in the water, and even shampoos and things like that are they'll maybe gunk up the pipe, but they're gonna keep it from calcifying as much.
I think he's talking about
In the fresh
calcifying.
water, in the copper.
In the fresh water.
line.
I'm sorry.
It's heated to a fairly low temperature, so it would be a lot less than, a high temperature water heater, but yeah, that could be an issue.
Is that still practical if your shower is a long way from your hot water heater?
Yeah. Yeah, you
You would have
could
to-
just insulate, this line that comes off of there going to the hot water heater.
You'd have an extra loop of water going to the shower then, right?
No, it would just go there's different ways to plumb it without getting into the details.
All right.
But yeah, you can run, once you preheat that water, you can run it a ways over to the water heater.
So does it, in terms of the actual water heating element, whether it's an instantaneous or something with a reserve tank, does it work better with one or the other? I mean, you were talking about the fact that with the shower, it seems like maybe it works best with an instantaneous because the warm water is coming down, preheating, and reducing the load. Is it as efficient if you're putting it into a hot water tank?
Be about the same. You're just preheating the water to either kind of heater. Another place to recover energy, I've gotten pretty rabid about putting in balanced ventilation, meaning supply and return and exhaust with heat recovery in houses now. It's just, the exhaust-only systems will meet the energy code, but I don't think they provide really good indoor air quality. Because if you had, this system now has, so these systems have a supply in each room where the humans hang out, like bedroom, living room, office, and exhaust from all the moisture-producing rooms, kitchen, bathroom, laundry. An exhaust-only system, people are relying on efficient bath fans to exhaust air out of the bathroom, and if you're running 80 cubic feet a minute out of the bathroom, it's coming in somewhere, but the problem is it's not necessarily coming in where the humans are. So you get two people sleeping in the master bedroom at night, it's cold out, the window's closed, you got a casement window, there's not leaking much air. So that bathroom fan, if you just had a bath fan, it'd be sucking from under the door, through the floor plates, or up through the basement, and not exactly where you want to get your fresh air, and besides that, it's not coming through the spaces where you live.
Unless you have passive inlets strategically located, which you should in the exhaust-only system.
So passive inlets are where you have a hole intentional hole in the wall in the bedrooms and other places where you want air. Unless the house is super, super airtight, I did some measurements on those things, and it depended, which way the air was coming through the inlet depended on which way the breeze was blowing. And it was very low dependency on whether the fan was running or not. So the houses have to be super airtight in order for those things to really function as intended. And even in that case, the wind, it's just slight wind will overcome them.
I have that system as described in an apartment house. So all sorts of different people go in there and they plug it.
They
As soon
plug
as
them up.
they feel the cold, they plug
Right.
it.
That's another
Whereas
issue.
in the heat recovery ventilation, that air is tempered
Yeah.
and they don't notice it.
Yeah, so this thing will, there's a picture of one of the boxes. You can see here's fresh air comes in this one, I think it is. And stale air goes out this one. The reason no, it's this side, sorry. The reason they're insulated is because, of course, the outside air is cold and the exhaust air is relatively cold once this thing extracts the heat. So it's got a fan that blows fresh air in and one that pulls stale air out. And in the middle, there's this core that's got a bunch of flat plates. So little passageways here, 1, 3, 5, 7, and 9 are air going one way, and 2, 4, 6, and 8 are air going the other way. So it exchanges the heat there without mixing up the air.
And what's your thought about ventilating the bathroom, either with that or a bathroom fan? Will you typically use your HRV to ventilate the bathroom, or would you have a separate bathroom fan in there as well?
I tend to just use this. The thing is that the airflow volume is much lower than you'd get with a bathroom fan typically. Like in my house, it's about 30 or maybe 40 cubic feet a minute tops when I hit the boost button in the bathroom. So these things typically run on low speed, and then you got a little boost button in the bathroom, so you can clear out the moisture a little faster. You hit the boost button, it goes up to high speed for 20 minutes or whatever you set it for, 40 minutes, 60 minutes. But it clears it out slowly. It clears it out fast enough that it's not going to damage the building.
Yeah.
But it doesn't get you that fast clear on the mirror, you know? So in high-end houses, we put both in.
Okay.
And, you know, the one provides a more continuous ventilation, and they'll hit the, 100 CFM. But then you need a good backdraft damper on those so that they aren't an energy liability.
Yes, yeah.
What's the difference between an HRV and there's another kind?
ERV. Okay, yeah, that's a good question. So in an HRV, H is for heat. So everything in here would be made of like a rigid plastic usually. Sometimes they're metal, but mostly they're rigid plastic. So no moisture gets through. You're recovering heat, but you're not recovering any moisture from the outgoing air. So, and then in an ERV, that's energy recovery, meaning total energy. So all these plates are made of like a paper-like material. Although it's usually plastic really, but it's sort of like, fibrous like paper, where that moisture will actually pass through. So you can actually recover moisture as well as heat. The times you want to recover moisture are when you're doing air conditioning. Because in the summer, when you're exhausting air that you've spent a good bit of energy to dehumidify in the house, and so it will actually dehumidify the incoming air to a certain extent. So in a house with cooling, or in commercial buildings with cooling, we use the ERV, the energy recovery. In houses that are moderately sized and moderately well filled up with people, or small size houses, once they get really tight, you've got moisture you've got to get rid of in the winter. And so you want heat recovery because you want to dump that moisture. And you actually use this thing to keep the moisture from getting too high in the house, the ventilation. If it's a 4,000 square foot house and 2 people, maybe you want to keep some of that moisture. So you might use an energy recovery. Just do this. It's the easiest, cheapest, best way to use solar energy. I'm a recovering complexity person. I struggle against this every day in my own work. And, I used to work with a guy, I was telling someone about all solar houses that had, 500 square feet of glass, and they had 10 tons of storage here and another 10 tons here, and there were fans and controls, and now, pretty much we've learned if you just really insulate the pee out of these things, make them airtight, need the ventilation, point it south, put some glass on the south, you're like most of the way there. Your load is just, goes down like this. And, it gets really tiny. It's just, this is just quite simple and works great.
What do you mean by sun temporary?
Oh, sun tempering. Well, people say passive solar a lot too. Passive solar implies there's some thermal storage involved. So you've got some massive element in the house. And in fact, this one does. It's got some concrete on the floor, but there's furniture. It isn't very well illuminated. It's useful, but it's not fabulous. Usually passive solar means you've got a lot of intentional mass directly heated by sun. Whereas sun tempering there's not really any mass. And you try not to overglaze it so you don't kill yourself out of there, although that's another preference thing. I like lots of glass. I like lots of heat in the winter in my house. I like it being in my t-shirt in March. I have an overglazed house. Mine, maybe you'll see a picture of it later. It's got more glass than this. And it does lower the heat cost. So let's look at some options. So here we're going to get into some nitty gritty. Okay, heating sources. We'll look at all these in a little bit more detail. Air source heat pumps, ground source heat pumps, solar thermal biomass, and some natural gas options, which could also be propane options. So the first question is, can you get away with a point source of heat? So the classic point source heater, I just set it down. Okay. the classic point source heater is a wood stove. Everybody's familiar with that. It tends to work better than other kinds of gas or heat pump point source. Point source meaning all the heat comes from one spot. The wood stove is such a high temperature, and it's putting such high temperature air into the space that there's a lot of driving force for natural convection to move that heat around the house. When you're using a heat pump, the air coming out of there is, I don't know what, 120, maybe 130. It's pretty low temperature, and so the house has to be really tight and compact in order for that to work really well. A propane space heater like a Rinnai, through the wall, seal combustion unit, it's somewhere in between. The air's a little bit warmer. It's a good bit warmer than a heat pump, but it's not anything like a wood stove. So when can you get away with this? You can get away with it where it's heat on the lowest floor. So in my house, the main floor is here, and then I've got a walkout basement that's real living space. Wood stove there, it doesn't do anything for the basement. It heats the upper floor just fine. So you need it on the lowest floor. Then the next question is, does somebody need to close the door? And this is like a home office. So the classic is home office and you got young kids at home. You probably need to close the door. And if that office is a little bit remote from that point source of heat, you're probably going to need some more heat in that office. As I get older, my temperature tolerance for like working at the keyboard goes down. Used to be kind of low 60s, now it's kind of high mid 60s. And also if the place is spread out. And I'll talk about that in a minute. Tolerance of temperature variation. So some people have been studying this and looking at how cold do the bedrooms actually get in these super insulated houses. And it's, 5 degrees colder if it's a fairly compact house at the coldest time of year. It's fine with me. It's fine with a lot of people. Not fine with everybody. Elderly, for example, might need more heat. And just, if you look in the engineer's handbooks about the comfort zone, it's, from this temperature to this temperature and this humidity to this humidity. And then so it's well-defined comfort zone. And then you look at the footnote, and the footnote says 80% of people will be comfortable in here. It's like, whoa. So success is defined as 1 of 5 people being uncomfortable. It's because the people's temperature tolerance really varies a lot. So if people are really not tolerant of it, you can't get away with this point source. Here's a house. This is a super insulated house. And this was some study on this was done by Building Science Corps, which they talked about it recently. Super insulated house. It has a heat pump here and one for the first floor, one for the second floor. The kind that sits on the wall. It's a it's point source unit. It's not ducted. And there's a bedroom over here. Bedroom here is cold. House is super insulated. It's just too spread out. It just didn't work well enough. It was, 10, 12 degrees colder in here than the rest of the house. It was getting a little much. So.
Of course, they have a garage door under the apartment up there as well.
Yeah, but they had lots of insulation in the floor.
Okay, you did.
Yeah, little packed, foot insulation in the floor. So you can't get away with this point source if you're not micro load or better. And that was sort of that middle of those 3 tiers I was looking at there, all of which were decent, but the middle or upper tier. It won't work if you need both heating and cooling on 2 floors. So you got 2 floors and you put heat in the bottom floor, you're fine. But in the summer, if you need cooling, you put in that cooling in from that same heat pump on the first floor, cool air is not going to go up the stairs. Spread out design, talk about that. Or if you need zones, you need tight temperature control. And for cooling, it doesn't work quite as well because there's a dehumidification issue in cooling. So you really need that air to move around.
How much does the air heat exchanger help these single point heat sources?
It doesn't.
Distributing heat.
It doesn't really, except for the bathrooms. The rooms where you've got some exhaust coming through, you're constantly pulling in, say, 30 cubic feet a minute of air. If you're pulling a little air into the bathroom constantly, that'll pull some warmed air in there. Unless there's view windows in the bathroom, unless there's a big load. But in the bedrooms, you're actually putting in fresh air. And even though the thing is recovering, let's say 80% of the heat, which would be quite good for one of those, if it's 0 outside and 70 inside, you're going to be putting in, I don't know, 55, 60 degree air in there. So it actually cools it, and, it doesn't help distribute the heat. So cooling sources we're not going to talk a lot about. So hot water options. Solar with electric backup, that's one of my favorites. I did not touch that up. There's now heat pump water heaters, and I'll talk about these things. You can heat it with a ground source heat pump. And this is not a de-superheater. This is actually using the heat pump to actually heat the tank. And the condensing water heater or zonable boiler. So those are kind of some options. There's coming back on the market. These started, I don't know, 20 or 30 years ago with condensing water heaters. They're now a new generation of them. Hopefully they're more reliable than the earlier generation was, the tank type ones. It's $1,000, $2,000, somewhere in there kind of option. So heat pump water heater, these have gotten to be all the rage now. So what this, over there. I'm going to unplug this thing in a minute. So a heat pump is like your refrigerator's a heat pump, right? It sucks heat out of the space inside the refrigerator and dumps the heat in your kitchen. It's a heat pump. So it's pulling heat from one place to another without getting into how it actually does that. It's a device that uses electricity and pulls heat from one area to another. If you wanted to use your refrigerator to heat your house, you could take it so that to your front door, stick it in the front door, and chink around it, open the door. It would cool the outside, and if the heat comes out the back of your refrigerator, it'd be heating your house. So you'd be using it for a heat pump. That's the way an air source heat pump works. It's sucking heat out of the outside air and dumping it into your house. A heat pump water heater sucks heat out of the ambient air, dumps it in the water with a heat exchanger, and, and then it gives out cool dehumidified air. So these things can have a pretty good coefficient of performance, meaning how many units of hot water do you get out for each unit of electricity you put in. So it can be 1.5 to 2. So you can sort of double the efficiency of an electric resistant water heater. There's a little bit of question. It's like, where does the heat come from? So if you got a very tight house and you don't have a lot of solar gain, and you got this sitting in here and it's cooling the house, then you got to run your heating system to make some of that heat up. So it's not all free. On the other hand, if you have a house that's got scobs of extra heat, you got a big old boiler in the basement that's dumping a lot of heat to the basement, that might be free heat that this can use. Or if you've got a really efficient house that's got a lot of solar gain, like 3/4 of the heating season in one of these little super insulated houses, you got extra heat. And so that might be a better place for it. Stephen Winters Associates did a really good report on these that you can Google online. That's got a sort of decision tree about when these are good and when they aren't. But you need some source of free heat, and you need to put it someplace where the noise isn't going to bother you. And I have a question about the lifetime of heat pumps. It's probably, I don't know, 15, 20 years maybe, if the tank, sort of lifetime of the tank.
So they're better in the summer, and then you could switch to a resistance heat or something else in the winter, where you're not robbing the heat from your heating plant, right?
And typically they've got a resistance element in them, and the better ones you have some manual control over that thing's running or not. Since these things are so current now, I put a little bit more in here about it. The efficiency, and this is the COP, so this was some measured data. It got almost up to 2, but it depends on how much hot water you're using. So this is the sweet spot for it. It's somewhere around 30, 40 gallons a day of hot water. If you're using less, the efficiency goes down. And the reason is that if you're not using the hot water, most of the load is to make up the standby losses. So the tank, you've got 120, it gets down to 100 and says, oh, heat it up to 120. And for the heat pump to boost 100-degree water takes a lot of work. Whereas if you're using a bunch of hot water, all of a sudden the tank's down to 50, and the heat pump's only doesn't have to work as hard to heat 50-degree water. So the efficiency is better when you're using it. But if you're using too much, then the electric backup, resistance backup has to kick in. This is my favorite hot water heater. So this is Wagner Solar. It comes from Germany. They're importing it, these guys in Boston. It's a drain back solar hot water heater. So drain back system leaves the collectors empty. It's closed loop. There's not air in here coming from the outside. You just fill the system up to here. And when there's heat to be had, the pump runs through the collector and comes back into the tank. And it's got an oversized coil in here to receive all that liquid when it's not running. So when it's not running, this is empty. This thing is a package. The pump's already mounted. The controls go right on the top. The connections are pre-insulated line set with compression fittings. There's no soldering involved. The line set's got an EPDM coating, which is a very durable rubber for outside use. The collector package is, you tell them whether you want them this way, or this way, and they send you the right fittings for it to sit on the roof. It should be $2,000–3,000 less than a regular solar hot water system. That's a drain back. So, and the great thing about the drain back is when you go away in the summer and your tank would normally overheat and your collectors would overheat, it doesn't matter because there's no antifreeze in it. That's all down here once the tank is charged. One of the problems with regular solar hot water heaters with glycol in there, if you go away for 2 weeks, that glycol stagnates in here and you get 300 degrees or more in the collectors and it starts to break down the glycol. And eventually it gets acidic and it starts attacking the system. And it means you've got a maintenance visit. So it doesn't break it down if you just keep track of the pH and you change it, but who does that? So anyway, I'm very high on this system. I think it's a great...
How big is the tank on that?
Oh, they make 70 and 90, I think.
Okay.
Yeah.
If that's $2,000 or $3,000 less expensive, how much is it?
I think you could probably get it installed for about $7,000 total, maybe 8, maybe 7. I'm not sure exactly. And then you take the credits off of that, which would be 30% federal and approximately 10% state. So 60% of 7,000, you'd net out at, I don't know, for $4,000, $4,500, something like that.
Who makes it again?
Wagner is the importer, Wagner Solar.
And it keeps a tank of water hot. It's not instantaneous, obviously.
Right, and it's got a backup. It's also got 2 coils in here too. So if you've got a boiler, you can use that for backup, and you can also put an electric element in it for backup.
And the panels come in different sizes and different size tanks?
There's 2 sizes of tank, and there's 2 sizes of panels, I think. Plus, they've also got some special anti-reflective glass, so they've got the highest collector efficiency rating of any of the collectors, which is only a couple % more than all the others, but it's something. Anyway, they've just been very smart about it, which I love. So
That tank needs to be below the collectors?
yes, must be below the collectors by some distance. Yeah, so if that tank had to go in the attic, insulated attic, you'd need to have a tall enough roof that you could stick the collectors way up on the top of the roof. Yeah, that is a constraint with this thing. They do have to be above. But usually that's the case. So here's the question. Do you want to do a solar hot water heater or a heat pump water heater? The other question that isn't asked here, which I could, if people are interested in geeking out on hot water sources, I have a spreadsheet that I can show you here where that compares which is better to buy, solar hot water with using PV and buying PVs for the backup, heat pump water heater and using PVs for the energy, or electric resistance water heater and using PVs. The cost of PVs has come down so far that it's actually changed this equation quite a lot about which works better or which has the lowest cost. So if you're headed toward net zero, one of your ways of evaluating how far to go in any particular item, whether it's an efficiency item or mechanical efficiency, is to say, what's the cost of the system and what's the cost of the PVs to operate it? Add those 2 together and pick the one that's lowest. So for this example, this is a pretty big hot water load, 4,500 kilowatt hours a year. That would be like 60, 70 gallons a day. That's a family of 4 or 5 even, maybe a couple teenage kids in there. So I'm thinking we can get this solar hot water system I just showed you for $7,500. Heat pump water heater, actually you can get them cheaper than this, but this would be a good one. you're still going to need some electricity, 1,200 kilowatt hours for backup or 2,000 to run the heat pump water heater. So that means that the PVs, you would have to buy a little over a kilowatt or 1.8 kilowatts to run the heat pump water heater, which would cost you at $4 per watt, which is a good price. You need to put in 4,000 of PVs to service the rest of the load from the solar hot water heater, or 7,000 to service the load from the heat pump water heater. Good so far? So the gross cost is almost 12,000 for the solar, 10,000 for the heat pump water heater, but we get some tax credit here, both on the PV and the solar hot water in this case. So the net cost is right around the same. And I think if, in this case, I would buy the solar hot water heater for two reasons. One is I think it's going to last longer. And the other is there's just nothing like having a tank of 150-degree water at the end of a sunny day. You fill up that tub, you sit in that tub, it's just like there's an abundance thing going on there with that, whereas with the heat pump water heater, it's a little different. Yeah?
Can you just talk a little bit about how, I mean, Vermont's fairly cloudy, especially in the winter.
Mm-hmm.
So, I don't know, what are you looking at to kind of make it worthwhile here?
Worthwhile?
Well, I mean, just if you're relying on the sun to heat your water,
Mm.
especially during the winter, you don't have a whole lot of sun.
You have backup, you got electric backup. So you've always got hot water.
But I mean, yeah, I guess I'm just saying, like in an area where you tend to be more cloudy, you have more to overcome. Does it still even out? Whereas like if you're in Colorado, and it's winter but it's sunny, the solar's going to work more effectively.
Yeah, I mean, you clearly get more out in the desert. We have plenty of sun here. You know, we're average 50% of possible sunshine here over the course of the year. In November, December, it's more like 30%. So most of this backup for the solar would be used during those cold and cloudy winter months. Am I answering your question?
Yeah, I think generally.
Okay. Like I say, if you look at this, if you had another line here for just electric resistance water heater, it's really interesting. I'm just looking at this for a really low load house. And it turns out for a low load house, if they want to go net zero and power it with PV, the electric resistance is just about the same as doing the solar hot water. For very low load, like 1,500 or 1,000 kilowatt hours a year, 20 gallons of hot water a day. Mm-hmm.
This is based on Vermont
Yes.
scenario too?
Yeah.
Okay. So to answer his question, you might be able to have a smaller system that would have a greater output and maybe do it at a cheaper installed cost
Right.
in the desert.
Right.
But
Or you get a higher solar fraction with this one.
Exactly.
Yeah.
Okay.
Yeah.
I'm curious because I have an electric hot water heater and my electric, and basically the house, not the house I'm going to build, but the house that I'm currently in, is all electric, and my electric bill averages about $30 a month. So why would I do solar hot water
Right.
if I can do resistance hot water?
Put up a couple PV panels. Would you check if she's taken a shower recently enough?
Well, your low load, is low load.
Yes.
Yeah. Yes.
Same with Wolfgar.
Yeah.
It uses electric
Yep.
resistance because it works for.
Yeah. Do you want to see what that looks like to compare all three?
Sure.
Okay. I did queue this up. Let me see if I can find it easily enough. Wait a minute.
Yeah, so what's the payback on these $7,000 systems?
It depends on your load. Anywhere from 10 to 20% rate of return, maybe 10 to 15, 8 to 15, 5 to 15, somewhere in there, rate of return. Oh, this is not showing everything down here.
The
Oh, there we go.
payback
Okay. Compare.
figures that are up there is the installed cost and after the credits and everything. But the solar would probably have a much longer life
Yes, solar will
on
have
the
longer life.
$7,500 investment than the heat.
Okay, so let's pick out a really low load here, 1,500 kilowatt hours a year. And the installed cost for the electric water heater is only $1,000. This is a good electric water heater, like a Marathon, very well insulated. But you can see your PV cost is higher. So your gross cost is is $6,500. You get some tax credit on the PV. So the lowest net cost is, in this case, is for the resistance water heater with the PVs at a very low load. Because the PV costs have come down so far. This whole thing has just turned itself on its head in the past 5 years. And then you can see if we put a really high load up in here, let's put that 4,500 load. That's a big load. Now the cheapest system is the solar hot water. The heat pump water heater is close behind, and the electric resistance is really expensive. So on the low loads, 1,500 kilowatt hours a year, which is very low. Sounds like where you are. Then the electric, if we go over here to the, once you bought the PV, this is this is considering you're buying the PV to make the energy. It's the lowest cost. We good there?
Yeah.
Okay. Where are we here? Solar hot water, okay. Here we go. Here was that discussion. It was here. Okay, we've already talked about that. Okay, so how to decide on a systems mix? So you need heat, you need hot water. Are these things should you get one system that does them both? Should it be separate? What do the options kind of look like? So the only way I know how to do this is going through the numbers starting with what folks want out of the house, but then looking at the numbers. So we can calculate a peak and annual load, and we can put together a matrix of the different systems. One thing to keep in mind is that on these very efficient houses, hot water is often as big as the heating need. So this is just a spreadsheet to figure out the peak load on a house, something you need to do. You can model annual energy use in a bunch of different ways. We won't get into that. But I use a simple model. Energy 10 is a good simple model. You can do it with a spreadsheet. Here, this is David Pill's house. And we just said, oh, well, look, depending on how tight we make this building, it's going to affect how many kilowatt hours a year we need. Because he was on a tight budget with a wind generator. So then I tend to look at it like this, and I'll walk you through this a little bit. And I just picked some examples here. For each particular circumstance, you'd have a different set of things you're looking at. But these are the ones, here's one example. So what I do is I look at the option for heat, cooling, hot water, what are the systems I'm going to use here. So let's say here's one option, air source heat pump with a point source of, so it's just a wall-mounted unit. This is a small, efficient house. That's a very low peak heating load. So this would be what I would call a micro-load house. A passive house might have, 12,000? Something? It would be lower. But there we're picking a micro-load house. So we could have an air source heat pump. It would deliver cooling as well. We could have a solar with electric backup or a heat pump water heater or resistance, and we sort of just went through that discussion. So in this case, these kind of systems are pretty discrete. The heat and cool does one thing, the hot water does its own thing. And here I've picked that Secusol, that's that drain back system. Biomass option. So this is one of my favorite Vermont solutions here. And we'll get into that a little bit more. Here's another option, ground source heat pump. We could have ducted delivery, water to air system, or it could be water to water with radiant floors. We could have the heat pump heating the hot water, or it could be solar. Here's a gas furnace, a conventional split system, meaning there's an air conditioner element and a gas heater. So this would be for some place that needed cooling. Be a ducted system. These things are inexpensive to install. This is probably your lowest cost system. And a gas tank type typical efficiency water heater. So this would be the home that wants the low installed cost. They get the propane tank from the dealer. They don't have to buy that. They're going to pay through the nose for propane, but they got in the house. They made it in on their budget. You can also do a high efficiency gas water heater with a fan coil, or you could, without air conditioning, and have a ducted system and have a gas high efficiency water heater. So the water heater would supply the heat for the domestic hot water, and with this fan coil unit, it would supply the heat for the heating. So now we just got it down to one burner instead of two. and then the one burner we got sufficient. So it's a step up from this one, but still using fossil fuel.
Are
So
those very common, the fan coil?
it's not all that common, but they should be more common because they can be really cost effective, and it allows you to use a much higher efficiency burner on the gas side.
Now, that could also
Problem is,
be-
it requires design. That's what's different. And so, busting up the place.
And you could also just use that through instead of ducting it, just go through a regular baseboard or something like that.
Well, the water heaters are not going to make that water hot enough for baseboard.
Okay, all right.
You could use an oversized panel radiator
Okay, yes.
or radiant floor. But a panel radiator would be a relatively cheap way to do that.
Okay.
But they need to be way oversized. I mean, if you run 120 degree water, you need 3 or 4 times the radiator that you need for 180 degree, which is what comes out of the boiler.
Yes, okay.
So, all right, so that's the systems, and we're assuming micro-load, heat recovery ventilation, compact floor plan. So let's look at some advantages and disadvantages. So this is the qualitative side of making these decisions. So here's our 4 systems here. Heat pumps can be powered with renewable electricity. That's their big advantage as far as I'm concerned. Otherwise, there's no carbon savings. I'm not really interested. People get they have lower energy costs. Like we saw when we looked at the fuel costs, it's cheaper to operate a heat pump than it is to operate something that burns propane or oil. But we haven't done anything for the planet unless we had the PV. Simple. These things are really simple because it's one installer. I mean, the gear is complicated on the inside, but that's the technician's problem, and they're pretty reliable, and they've been all over the rest of the world for decades, and they've just been here in the last decade or so. And they're less costly than ground source heat pumps. Fans do make some noise, although they're pretty quiet as fan things go. And you got this ground-mounted or wall-mounted thing on the outside of the building. I'll show you some pictures. So the ground source heat pump, again, we can use electricity, very high efficiency. It's got a low peak utility draw compared to this. This air source heat pump in the middle of winter puts a pretty good pull on the electric utility. So in terms of societal considerations, you're bumping up the winter peak. Now, Vermont used to be winter peaking electric, but in the past probably 10 years, now the summer is the big peak. So it's not as big a consideration. Where is that? Yeah, so this has a lower peak utility load. Of course, these have no peak utility load to speak of. Gas furnace, if you had natural gas like Burlington or someplace or other parts of the country, this may make sense, either of these, from a cost point of view. It's conventional trades here. You can use an EC, electrically commutated motor, one of the new efficient motors in the fan to reduce energy use. And these, the advantage here is we only have one burner for both heat and hot water. And you can add AC to either of these if you want.
Andy, why is the boiler not an option for you on yours?
It could be a boiler, it could be an option. And I'll actually show you a house where we're doing a little boiler as one of the examples.
Where are you finding a boiler that's 20,000 BTU?
I'll come back to that. That's a really good question. Where can you find anything that's that small? The heat pumps you can. But yeah, the boilers you have to do some tricks, and I'll show you, and if I forget, remind me.
Is the fan coil what a unit ventilator is?
Yeah, well, the unit ventilator in a classroom usually has an outside air component. This is just a fan. It's just like the radiator of your car. It's got fin tube and a fan behind it. And you run the hot water through the fin tube and run the fan, and you get some heat. So disadvantages, this expense, that's the big one on heat pumps, ground source heat pumps. And a coordination of trades, there's a bunch of people involved. A lot of design required. And the fans can be noisy if it's air delivery. On the gas furnaces, they can be really noisy. And the new ones can be even noisier. They've tended to make them smaller and more efficient. And one of the ways they've done that is to bump up the air speed. Well, faster air means more noise. And they can be really nasty if you're not careful. Hard to find them small enough. If you use instantaneous gas, hot water, watch out for hard water. Not for super low load homes. So the fan coil You can, it does require design, very careful design. You need to test for hard water if you're going to be running potable water through there, but you can isolate them. And design is required for this. Meaning somebody's got to think about duct sizing and picking the fan coil and picking the pumps. So you're going to have a few $100 in design, and somebody needs to be thinking about it. So that's the reason that conventional homes use this approach. It doesn't require a lot of design. All right, what does it cost to put these in? Do you want to run through the gory details or just look at the totals? What? He wants, can everybody else stand it if we do some detail? All right, air source heat pump. You can get a single unit for $4,000. People get them cheaper. You can go and buy it at the distributor and then go hire somebody to install it and get it cheaper. But if you go to an HVAC guy, he goes to buy it, he marks it up, he puts it in, you have somebody you can go to when something goes wrong. But it costs you more. And that's more this kind of price for a single unit. And I got $4,200. I got a small unit in recently. No ducting, ERV or HRV, ERV if it's cooling. You know, it's kind of this kind of price.
Andy,
Yeah.
you said you got a air source heat pump recently. Is this for your home?
No, for another home. Yeah. So we're looking for heat cost here of $6,500. Add some markup if it's being done by the general contractor. Maybe we got $7,300 in there. We had a net of $4,700 for solar hot water. We're added up to $12,000 here. Ground source heat pump, whoa, 18 grand. And that's being careful. So everything else is pretty much the same. 22,000 total cost. So 12 for the air source, 22 for the ground source heat pump. You can see why these new air source heat pumps are just eating a lunch of these other systems. Gas furnace, cheap, $13,800 with a gas water heater. This fan coil an efficient gas water heater with a fan coil. We can do that for roughly the same, maybe a little less, maybe not. These are kind of equivalent within the error of this estimate. But this is a lot more efficient running, but does require some design. You have to have somebody good designing this one in particular. There's lots of people around that know how to design furnaces, but not a lot that know how to pick fan coils.
Andy?
Mm-hmm.
So let's just go back to the air source heat pump. If you're saying in Vermont, most of us don't need the ERV, so would you subtract that $2,500?
Well, no, you'd use HRV, so you still need the ventilation. Yeah. And this is a pretty low cost for these. Often, this is a simple house. In a spread out house, this cost will go, what, $3,000, $4,000? I don't know what people are seeing. Yeah?
Do you think the air source heat pump should have the 30% tax credit made available for it?
I don't think so, because they're just in a more efficient way to use electricity. It's not really renewable energy in my book. The ground source heat pump, you can argue that the heat you're pulling out of the ground is the solar heat that hit the ground the previous summer. But mostly they take a lot of electricity to get that out of there. So I don't call them renewable, and it doesn't make me friends with some of the heat pump people. But
If you add the solar necessary to zero out the air source and the ground source,
yeah,
where does your total cost end up?
without going through it, you've got a lot to play with here. You've got $9,000 to play with. Well, not quite, because this will take some PDs too. We can look at that in the next slide where I've got some costs here. Okay, so what are the operating costs going to be? So I picked a home where the annual heat load is 9,000 kilowatt hours a year. That's the load, remember, not the energy. Cooling load 4,000, hot water 4,000. So it's this is not a single person. This is a family here, and some costs there for fuel. And some assumptions. I'm saying that the air source heat pump will get a COP of 2.5 or an efficiency of 250%. The ground source COP of 4, that's really good for a ground source. That would be a water to air system, that's air delivery. The water to water ones aren't quite as efficient. I wanted to give it the benefit of the doubt here. High efficiency gas furnace and water heater, very efficient. Conventional water heaters are only like 60%. They really are not that great. Electric water heaters are efficient on site, but of course primary energy isn't. We talked about that. So here's the COPs that we used for cooling. Okay. So what did it cost to operate these 4 systems? Here's how many kilowatt hours we needed for the heat pump, for the ground source versus the air source. And to answer your question, John, so it looks like we need, say, 1,400 kilowatt hours more, maybe 1,200 watts of PV at $4 a watt. Well, net 3, maybe it's 3,500 bucks difference. And you can see the difference in the system cost was $8,000 or more, no, almost 10. So, so the total energy consumed for hot water here, we've got solar and electric backup. It's almost 6,000 kilowatt hours a year. It costs about 900 bucks to operate. The ground source heat pump system is going to cost about 650, so it costs less to operate. Natural gas here is 930 bucks. If you're doing this with propane, you can double that. So propane here would be, $1,800 for heat and hot water, or $1,500 with a higher efficiency burner. Very efficient house. So this would change if this house was not efficient. So who's the person with the log house? Yeah, so it's a different equation in the log houses. You've got a big load in there, unless it's really tiny. You'll need to rerun these kind of numbers to make sense out of it. And the span coil, costs a little bit less and costs less to operate than this one, but there's some design cost in there. I didn't add the design cost. Let's say these two really cost similar to install, but this one's just lower operating cost.
And what do you think that design cost would be? Are we talking $1,500?
I just did, let's see, for the fan coil unit system, maybe 1,000, maybe 1,500. It depends where you go, All right, want to see some examples? All right, okay. I've got enough examples to keep you here for quite a while, so just tell me when it gets to be too much. Okay, this is Colin's house. Colin's a musician in Montpelier. Colin McCaffrey, great musician. He's my guitar teacher. I traded him design for guitar lessons. He said, I have this is almost 10 years ago. I have $100,000. I got to get in a house for $100,000. Myron Dorfman and David Vistering built the house. They're very reasonable, at least they were at the time, and probably still are. And you can see, nothing fancy here. Box that's got knee walls. It's got 2x8s in the walls. It's got low E windows, not triple. This isn't a micro load house, but it's small. So it's what, 700 square foot floor plan, 750. So here's what I did for him. Let me first show it to you like this. He's got a wood stove, and then he's got a Renai water heater, but we use the water heater cleverly here. And Mark Rosenbaum had done this once before, and I took a cue here. We're using the Renai, here's the Renai, to heat a tank of water. And this gets to that question of how do you get to how do you heat a low load house with a boiler? So Renai is essentially a boiler. These things will put out 100,000 BTUs an hour. And the reason they're so punchy is that when you're running, 6 gallons a minute of hot water, it's got to have some, some grunt to heat that water. This is a water heater that's made to be heated by a boiler. So it's called an indirect water heater. It's made by a company called Triangle Tube. Will McLean also sells it. It's a tank in a tank. And the boiler heats the space between the two tanks, and your domestic is in the middle. And that's how it works. So it's got a bunch of heat exchange surface. In terms of hard water, the inside tank here is very thin metal, and it's like wrinkled like this. And so as it expands and contracts, it knocks off the scale down the bottom. It's a pretty cool system. And the nice thing here is we're able to use this instantaneous water heater with hard water, because the only thing it's looking at is captive water in here. We're not running water through here all the time. So the Renai heats this space around. That heats the domestic hot water, so that goes out to the house for hot water. And then we've got a couple radiant zones in the floor. He had to have one for his room with all his instruments, because it's got got to keep a constant temperature in there, and the other zone's the rest of the first floor. So here's a place where he had to have zoning. You know, he couldn't deal with a point source. Yeah.
If you're doing it that way, why don't you use an open system and avoid that whole problem?
Open system.
Where your hot water and your heating water is the same.
Well, it's against code to do that because.
Not in Vermont.
Uh,
Vermont's had the International Planning Code for 10 years.
Yeah, you can do that. I'm not a fan. I'm not in, you know, I don't want water sitting in floor tubing for 6 months and then being used. Yeah. You can get away with it, and a lot of people do. I don't do it. I like to keep them separate. So the zones of radiant run off the water that's in this space around the tank, and there's a mixing valve here to keep the temperature right. You can see there's a little bit of plumbing involved, but it's nothing that unusual.
What's the cost on the Renai unit?
Oh, I don't know, 1,000, 1,200, 1,500, does anybody know? This is a drawing I just finished the other day. I took the drawing, this one's using a Bosch water heater. You know House Needs here in Waitsfield?
Mm-hmm.
They sell this, they've got a bunch of these Bosch ones that's a discontinued model for under $400. And it's meant as a boiler. It's not meant to be run as like a Renai instantaneous water heater. It's meant to heat a tank of water. So this is that same system, it's just a fancier drawing. So this one is using a Bosch, it's seal combustion, heats the space around the inner tank. That's what we draw off of to do the radiant zones. And then we take the domestic out of the inner tank there. And this is for an off-grid house for when they're not home. And when they're home, they're going to use a wood stove. So that's Colin's house.
A wood stove to heat their hot water? Or is that-
Wood stove for space heat. And then this thing will heat the hot water.
Because it looks like, are those just wood stove tools that are sitting next to the wood stove, or is that piping to heat hot water out of there?
Actually, that's my wood stove in my old house. It's not Colin's wood stove, and yes, it is piping.
Okay.
But actually, he's just installing a couple loops in his new wood stove to heat his hot water because he's tired. He's got 2 teenage girls and him and his wife, and he's tired of paying the propane bills.
Mm-hmm.
He doesn't own the tank.
Now, is he using a standby tank for that, a preheat tank, and then feeding that?
Preheat, yeah.
Regular
Yep.
storage tank?
Yeah, but the preheat tank will just feed into this propane-fired tank, yeah. Okay, so pros, inexpensive, tolerant of hard water. We got zone radiant floor out of the deal. 1 burner, seal combustion, compact. It's all stuck in a closet. The whole thing didn't take any room to speak of. There's some system complexity. It's a bit unusual. It's propane and it's CO2.
Quick question, I also know at House Needs they sell electric boilers for small systems
Do they?
Yes.
Uh-huh.
that do this essentially. So you wouldn't have the propane
Yeah.
cost.
But electric would be probably higher than propane.
Well, maybe if it's PV tied.
You could make it back. Uh-huh. This is Randy's house. So 2,400 square feet, a little bit bigger load. We're sort of pushing micro load here. It's sort of 3 floors on a bunch of different levels. It's kind of a crazy house. His goals were a low-cost system, inexpensive to operate, renewable ready, and single zone. Single zone was good for him. His primary heat's going to be a wood stove. So again, that's my wood stove. His stove is not going to have pipes in it. So we're putting in one of these heat recovery ventilators. This one's Venmar Echo, which is what I have in my house. It's good because it has very low energy motors and decent efficiency. It's pretty good efficiency on the heat recovery, and the motors are very low watts. Mine runs I run it on the lowest speed. It runs 22 watts, which is really quite low for whole house ventilation. So it's got a wall-mounted single point source in the house. This is what one of these things looks like on the outside. This is wall-mounted, which you can do, and it was under an eave of a metal roof house. So we put this thing over it so that this is at a different house, so that the snow would stay off of it. These things, by the way, you can't put these out where they get buried with snow. They don't get any air over them, no go, they don't work. We're hoping to put solar hot water on here, but you know, I think he's just going to increase this, but his final decision was increase the size of the PV and put electric resistance in. Very simple system. So this has changed a little bit since, so pros are simple, wood stove primary heat, renewable ready. The bank was not super happy with a point source of heat, and we may end up going with a ducted unit on the inside with like 3 registers. The bank needs to see a ducted heating system. Okay, we'll spend a few $100 and give them a ducted heating system. One zone for 3 floors. We think it's going to be fine. They're on board with variation in temperatures, and when I do one of these single point source heating systems with a owner, I try and have the conversation at least 3 or 4 times, and at least once in writing. You know, you're going to see some temperature variation. You okay with that? You didn't answer my email. Were you okay with it? You know, if I wanted somewhere that they said, we're okay with this, you know, so. Cons, yeah. CO2 emissions until he installs PVs. So this is a Benson Wood. This is at one of their Unity homes. I did some work for them on this. Their goals were low cost, inexpensive to operate, just like Randy. Single zone. And AC. So it's just, so here we're doing electric resistance water here. That's a Marathon water heater, which is, it's got a polybutylene tank, so it should last a quite long time. They give you like a lifetime warranty for the first purchaser on it. And it's got 3 inches of foam on it, so it's really well insulated. This is the outside unit. Now we're using a ducted inside unit here. And that house will have it'll have 1 main trunk and a couple of little branch ducts. I don't know, there'll be $600,000-$800,000 in the ducting. But we get one zone, but we get it on 2 floors. Since we duct it, we can get both heating and cooling up and down, since it's ducted. So that's the advantage there of going ducted for them. Relatively inexpensive systems. This is David Ellenbogen's house. Bill Hygus and Hobie Guyan built this. Designed to be near net zero was his goal. He wanted to burn some wood. And he needed zoning. He was not okay with temperature variations through the space. He wanted to be able to close the door in his study, and he was willing to pay for that.
What is the pitch of that roof in the PV?
I don't know, what is that, 10 and 12 maybe? You know, it turns out for net metered PV, there's a really broad optimum on the angle, anywhere from like 45 degrees down to even 20, because the lower pitch gets more sun in the summer, and you really, with the net metering, you just care about the annual total. If it gets too low, the snow's going to stick, so that's an issue, but this one is probably up around 35 degrees. So here's his system. We've got a Marathon, we've got solar hot water. You can see the solar hot water there. He's got a bigger heat pump. This one now is one outside unit that handles a bunch of indoor units. So one room has a wall mount, one's got a ceiling cassette mount, so it's flush with the ceiling in the living room because he didn't want to look at it. And then there's a ducted piece that serves, I think, the 2 upstairs rooms share a zone.
If your solar hot water has an electric resistance backup in it, why do you need the Marathon too?
A 2-tank system's a little bit more efficient.
Okay.
And you can set it up where there's a tiny little circulator between the 2, so that when this tank gets hot, rather than having to wait to draw water to bring that into the tank, the little circulator says, oh, the solar tank's hot, the other hotter than the backup tank, dump some of the heat in there. So you can make up your standby losses with the solar that way, which is what we
Is that
did.
a sidearm transfer between the 2 tanks?
No, that's the piping that does the transfer from one to another. Yeah, that thing's got an integral heat exchanger in it, the tank on the right. So he has all renewable fuel. He's zoned. The big con is cost. This is David and Hillary's house over in Charlotte. Nice passive solar exposure. It's got concrete floors. This really is passive solar. He has polished concrete floor on that first floor. And so all of that glass, and it's a very modern spare house on the inside. So the sun really sees that floor. It really shines on the floor and does quite a good job. Pretty low load house.
Andy,
Mm-hmm.
have you ever gotten, after making all this investment to have the sun heat the floor, do you ever get honest response as to the comfort in that room? Or does it cycle to where when the sun's out, you can't be in the room? And then several hours after the sun goes down, now you can go back in the room, it's comfortable, you're not blasted out with solar heat?
Well, in my house, which is overglazed like this without all that mass, it's got some. I open a window when it gets too hot. So people have to be tolerant of temperature swing for a passive solar house. And that's another conversation that I have repeated times with people who want lots of glass on their house. Say, it's going to be 80 degrees in here when the sun comes out, unless you open a window in March. And maybe not in December. December is probably fine. And they'll say, and it's going to be hot in there, temperature's going to go up and down. You're going to be happy? Yes, I'm going to be happy. So the next time we get together, we have the conversation again and again. And with that, I haven't had an issue with it. And then, Angela moved in and David moved into this house, and I said, how is it? We love it. So it's one, it's that temperature box. Some people are happy up at one end, and some aren't. These guys have a wind generator in back. This looks like a toy wind generator because of the perspective. It's really several hundred feet back from the house, and it's on a 130-foot tower. It's a 10 kW Berge, and it net zeros out this house. This house got the first NESI Net Zero Award. So we've got all this stuff in here. Ground source heat pump, 3 zones of radiant heat, 10 kW generator. This is a complicated house. The mechanicals are complicated on here. So there's a ground source heat pump. It pulls heat out of the well water. So we take water out of the ground, extract some heat, dump it back in the well. Variable speed drive on the pump. The heat pump will heat one of 2 tanks. If the hot water tank is calling, it goes there first. If that tank's happy and there's a call for heat, it goes to the radiant zone. And again, you can see I separated them with a heat exchanger. I don't like mixing those two. And actually, that schematics is not all that complicated. But any question on that?
What do you do if you're calling for hot water and heat?
You prioritize the hot water. Super insulated house. It takes an hour to heat the tank. Even an hour, it's not going to take an hour. But if it took an hour, you wouldn't even notice.
And then are you circulating that through baseboard or through?
This is radiant.
Floor?
Radiant in that it's concrete floor. It's 3 or 4 inches of concrete poured on top of wood frame floor on the first floor.
Does the radiant circulation redistribute that sun heat that is in there? Do you have it timed or somehow?
You could do that.
To do that?
You could do that.
As a collector.
Yeah, you could recirculate. He's saying because the sun shines on a third of that radiant floor. If you ran the circulator, you could distribute that heat through there. I haven't tried that. It's a question. Yeah, might be worth doing. This is what the piping looks like. Now, David's house, it's all spread out. This is the same system, but in another house that it had all fit in a closet. It gives you a headache trying to trace the piping around. These systems are just fairly, there's a lot of piping involved. Let's see where, yeah, and here is the electrician, the plumber, the well driller, and the plumber. They all had to be involved. You can see all the piping. That's that same mechanical room that's in the other picture. They all had to be coordinated. And that's tough. One of those links in the chain doesn't show up, screws up, things don't work. This was some measurement I did on solar hot water systems, looking at this whole system coefficient of performance. So when you buy a heat pump, a ground source heat pump, they'll tell you what the coefficient of performance is of the box, right? Of this box right here. And it's usually quite good, like 5. I mean, it's a really great number, right? Well, but you got to run the pump to bring the water in. You got to run these pumps and they all take electricity. So when you look at the manufacturer's rated COP for that box was 4. I measured the COP of the unit at 3.5. Okay, that's not bad. But if you take in all the other electricity that's needed into account, the whole system is running less than 3 on average. So, you know, water-to-air heat pumps can be a little bit better than the water-to-water. So it isn't always this low. And but when you talk to the heat pump people, you know, while I was doing this research on this stuff and running all these numbers and doing these measurements, you know, the heat pump ads were coming out. Get rid of your heating bill. It's like, no, that's not what happens. You turn it into an electric bill. And if it's a good system, you can turn it into a low electric bill, but it's still a heating bill.
Andy, does the installed cost, you know, it was so high in the example you showed, was that because they were drilling for the ground source heat pump? You know, if you did the well water version that you just showed here, is that cheaper?
That was considering like this.
Yeah. Okay.
Yeah. I mean, I went to look at a little house where they had $30,000 in one of these systems. Yeah. Which is not unusual for one of these.
Yeah.
They get really complicated. And there's a bunch of places where you can trip up on the energy side. Like this one I went to look at. This pump that heated this tank was running 24/7. Oops. He was running several hundred watts. I called up the installer. I said, "What are you doing?" He said, "Well, we don't want to." I don't know. He had some reason. He didn't want He didn't want an added complexity in the controls. I think was the best reason he could come up with. But it was costing them, I don't know, 1,500 kilowatt hours a year. I mean, it's killing you. And if you oversize these pumps, it also kills you. So these systems require pretty sophisticated design to be efficient. Many devils in many details. That's the main con. They're very efficient in operation, and you get great, you know, results out of them. But there's a lot of complexity. The heat pump will only do limited. It'll barely make 120-degree hot water. They just can't work that hard. The hotter that's trying to heat it, the harder it has to work, and it's a limit. And so it's barely acceptable hot water temperatures, and it's this coordination of trades and the cost issue. Okay, we might be getting to the end here. So this is where I live now. This is a little co-housing community, 6-unit, with the common building, and my house is back there. Goals were 0 carbon, so not net zero on electricity. We're counting wood and pellets in this case as 0 carbon. But not too expensive. We want zoned heat. We wanted to be able to build the individual. We wanted a central system that we could build heat for the different units. They run from 1,200 to 1,800 square feet, so it's about a 600 square foot footprint, but it's a full walkout because they're all on south-facing slope. So there's my house with all the glass. See, I'm like glazed like crazy. These guys are a little more sensible. They're a little more sensible. This is a connector between the 2 units. Here's the hot water on up on my house. So we have a central Tarm wood pellet fired boiler. There's passive solar on all the houses. They all have HRVs. Some of them have solar hot water. Here's the underground piping that goes between. So we saved some money and we insulated the pipe ourselves. It's like a 2-inch PEX, and we put 1-inch wall thickness insulation on it, and then we jammed it into 4-inch thin wall PVC, glued up the joints, and that's what we did for the buried pipe, and saved a few bucks because the pre-insulated flex stuff, it gets pricey. Here you can see, what is this line? Oh, this is a communication line. We just buried a 4-inch empty conduit between all the units for something. And there's a control line in there for the... Yeah. Well, when our neighbors first moved in, they weren't in when we lived there. She kept hearing some like voices in the basement and music coming from somewhere, and she thought she was going nuts. Well, it was. We finally plugged the ends. But we've got a little homemade seltzer machine in our basement, you know, with a tank of CO2 and a regulator that you can, with a Schrader valve on the bottle cap, and you can, you know, make your own seltzer. And we're going to run CO2 line over next door, so we'll have a community carbon dioxide line. Yeah, and then we've got runtime meters on each zone. So every time we get a delivery of pellets, there's an automatic hopper for this thing. We read the meters and we allocate the heat use accordingly. And they're like, 25 a whack instead of, say, you got maybe 150 or 200 installed here, whereas a BTU meter per house would cost around 1,000. So the pros are, yeah, local, relatively local. We get them from New Hampshire. We got wood stoves in most of the units. We can bill. There's one burner for 7 buildings. It was about $50,000 to put together the whole boiler system and the piping. So that's fairly reasonable per house. And then you also had to pay for the distribution in the house. There's a bit of complexity in design. There's, it's piping and pumping, and that all had to be designed. And there's some standby losses. And this particular boiler takes a cleaning once or twice a week. You open up this thing and clean out the fire tubes. 6 families, it's not a big deal. You sign up, and twice a year you have a month of cleaning.
What, just carbon buildup, soot?
Ash.
Ash. Oh.
Ash, yeah. It burns clean, hardly any soot.
Yeah.
If there's soot in there, something's not right. And you clean the ashes out of the firebox too. The new ones now, we had some money left in our initial account. I tried to convince people we should get a new Froling because they clean themselves. They're way more efficient, but another $20,000, people couldn't see it.
So where's the boiler in your house?
It is in the common building here, right here. So there's underground piping goes over here, and then it splits and goes both ways. So this is, I think, 250, 300 feet here, and another 130 feet here. So there is some significant standby losses. And it's a relatively high percentage for us because the loads are so low. Ordinarily, you think of this underground piping loss of maybe 5–10%. For us, they're like 10 or 20%, but it's because the load is low.
But it's not enough to warm the soil to grow, tropical fruits or something.
No, but the standby losses from that tarn heat the whole barn. The barn is well insulated. All the places are well insulated.
Did the houses all use the same type of insulation there? Did you have standard for the different?
Double wall, 12-inch walls. John came in, damp sprayed the walls and dense packed 16, 18 inches in the roof. Except for one house in the end where he did his own thing. He was a builder and built it differently. He hand packed his own walls with cellulose, hand done dense pack.
Oh, really?
Uh-huh. And in the slopes too. You could see a few voids in there, when they get the frost on the roof, you get that sort of nature's IR camera up there, when you get a little light frost, you can tell where there's thermal anomalies in the roof, right? And you got a few in there.
Did he work for Ben & Jerry's? Curious.
Hand packed. But even with dense pack, we got a couple of spots. It's hard. John came back and pumped them all in, fixed them up. But okay. Oh, there's one more. Okay, one more.
Sure.
How you doing? So this is my mentor is Norman Saunders, who I studied with in the 70s, who did all solar houses. These hugely complex things that were really interesting and innovative, and he did a bunch of them at the time. Well, his son wanted to build a solar house. And I said, we're not doing like Norman did anymore. But what we did here is this is a rental house in Keene, New Hampshire. It's just a simple box, very super insulated, triple glazed, it's our micro load house. And we've got 240 square feet of solar on the roof, solar thermal. His goals were almost all thermal from solar and zoned heat. So we did a big drain back system. This is a soft tank in the basement. I think this is a 600-gallon tank. So it's a drain back. So this is atmospheric. It's got a lid, but it's atmospheric pressure. You pump water up in here when there's heat, and when there's not, it all drains back into the tank. And there's heat exchangers in it to pull out domestic and pull out space heating. Pull out domestic.
Was that a custom built system or did you buy them? Those coils?
They are, you get those from the tank manufacturer.
Oh, okay.
Yeah, they sell the coils. So here's a schematic here. So I've exaggerated the tilt to show you that they drain back into the tank. there's 2 pumps here. And in order to fill this thing, both pumps run, but then one cuts off, because once it's filled, it siphons itself, and you don't need the pumping power. Nowadays, you can buy variable speed pumps that do this in one pump, but we didn't have that then. So whenever there's heat, we're heating up to 600 gallons of water. Then there's a coil in here with a little circulator that'll heat up the domestic hot water here, from here whenever there's solar hot water. And then we've got a fan coil here to run space heat for the main floor upstairs. We put radiant tubing in the basement. The radiant tubing runs right off the tank, the soft tank water, so we can run that water through the tubing, heat that floor. Because this is radiant heating, floor heating with concrete is a good match for solar thermal, because you only need like 100-degree water, and you can even get heat out of 80 or 90-degree water. So solar thermal systems need the distribution to be very low temperature in order to be able to get the best use out of the solar energy. So the radiant's a good match. And then we did a fan coil with a very efficient motor in the fan and sized it to be quiet and so on. And it's got 2 coils in here. This is Mark's thinking. This is really clever. So the first coil, let's see where, yeah, this coil comes from the tank. So if the tank is warm enough to do this, like 100, this is sized for 100-degree water. If the water in the tank's 100, the fan will come on, the solar water will circulate, and it will heat the house. But if the tank is, let's say the tank's only 80, well, it's still hotter than the house, right? So we can run water through this coil, but supplement it with water from the water heater, so that when there's some heat available in here, even though it's not hot enough to heat the house, we can still take advantage of it in the fan coil unit.
The hot water heater is getting solar from the tank.
And it's electric backup.
And it's backup, so you always know that you've got your heat.
You've always got hot water, yeah. And here you can see those 2 pumps. Let's see, where are they? 2 pumps in series going up to the roof collector. They're pretty hefty pumps.
Whose pumps do you like to use?
Oh, any more of these Wheelo pumps now are the best. They're the lowest energy. Grundfos is pretty good now, too, between the 2 of those. But the Wheelo, I think, is a little bit lower energy.
Have you done any of these fairly evolved systems with off-grid houses?
The one I showed you that was Colin's house, we're doing one just like that for an off-grid house right now.
And what are you using for batteries?
I don't do the battery part. I get somebody who's smart on PVs. I don't know enough about all that stuff. And the system is mostly a backup system, the radiant floor system with the Bosch, it's the one with the Bosch boiler. And we went through and figured out how many watts it was going to draw. And it was a fair number of watts, but it's not used that often. It's used when they're not home, which means they're not drawing other electricity. And they've got a backup generator besides, so if the batteries tank, it'll automatically charge up the batteries. So and I worked with Hilton Dyer on that. He did the PV stuff on it. He's very smart on all this stuff. He said, you just use you can get a sealed combustion tank type water heater that requires no electricity. And that's kind of the natural choice. And I've used one of those in another off-grid house. The problem is they're like 50% efficient. They're just dogs. And if they're using any hot water, it's going to cost them a lot to operate. So we went to this other system and figured that they would have enough electricity in their batteries to run it. I think we figured it was 1,500 watts at the coldest day of the year, coldest hour of the year. But mostly we run a quarter or third of that. And domestic hot water was about 300 watt hours a day, we figured. And he's got several kilowatt hours a day to play with, so it looked like it was okay. And it saved a lot of propane. Yeah, but for off-grid house, if you really, I worked several years ago on an off-grid house where she had 600 watts of PVs, that was it. And so that one had backup, it had a wood stove with a backup of a propane through the wall heater with a pilot, just, you know, dog of efficiency. And the same water heater I was just mentioning that was also a dog, but didn't take electricity. So she was off, you know, she was off grid, but she wasn't off propane. So this house, yeah, pros are, yeah, it's running on the sun. It's not 100%, by the way. There's electric backup for the heat, too. It's a complex system. And the owner has to be conscious of what's going on there, and the renter there was not. And they ran up the electric bill quite a bit. And it's not inexpensive to build. About $30,000 for that system, and we got a pretty good deal on it. So back to the general principles. Capture waste heat, humans need fresh air, make it simple, use renewables, and pay attention to goals. Is your head spinning?